Okay, welcome to lecture number 14. So, we will continue from where we left last lecture. Let us recall what we did. Remember, we calculated that n, the number of electrons per unit volume in conduction band, is equal to n c times 2 by root pi this Fermi Dirac function of order half, where n c eta c was equal to E f minus E c by k b t. And similarly, we had derived number of holes per unit volume, that means holes density was equal to effective density of states of valence band for holes or electrons for that matter, Fermi Dirac function of order half eta v, where eta v was equal to E v minus E f by k b t. That is what we had derived, and then what we started doing was that we started approximating this Fermi Dirac function, the integrals rather, not function, rather this particular integral we had started evaluating as to what these two integrals were may be equal to. We started approximating it. So, in that context, what I had done was that I had plotted this graph for this function as a function of eta, and here is eta, and then this is some values here, and this red line, this red curve was this particular function which appears in these equations also. Then what I also did was I simultaneously plotted e to power eta right here, and I was saying that at least for eta less than minus 3, as this value right here on the left of this value, we could approximate this function as equal to e to power eta, as this indicates. In fact, you could pick this approximation at minus 2 also, maybe minus 1 also, depends on how good approximation you make. So, I am taking, if I am stating that if it is less than minus 3, then this particular function, this integral, Fermi Dirac integral, could be approximated as e to power eta minus n. All right. So, if so, then now we continue from here. Then in that case, how would you approximate n? So, what are we saying? That means if eta c is less than minus 3, then I can write n to be equal to n c times e to power, I can write it, replace it by eta c. So, I can replace e to power eta c. I can replace this function which is right here, this integral which is right here, I can replace it by e to power eta c. And since we know what eta c is, I can therefore write n being equal to n c times e to power E f minus E c divided by k b t. So, here is n. Here is the value of n that we can derive as n c times e to power E f minus E c by k b t, under the assumption that n c is less than minus 3. We can further look at eta c is less than minus 3. So, we can further look at this. This is when, what is the condition? Condition is, that means eta f minus eta c by k b t should be less than minus 3, which means E f minus E c should be, energy c should be less than minus 3 k b t, which means I can write this as E c minus E f as being greater than 3 k b t, and that means E f Fermi energy should be less than E c minus 3 k b t. So, that is what our requirement is. If so, then we are okay. All right. So, EC, or you can look at this or this, either way. What that means is that if I plot this band diagram, if I plot this band diagram as follows, if I have something like this, this is EC and this is EV, as long as Fermi energy lies 3 kBt below EC level, that means as long as Fermi energy lies, if this is 3 kBt, then as long as Fermi energy lies, EF lies below this, then this approximation can be used. This particular approximation can be used, and n will be then given by this. If not, that means if Fermi energy lies above this, then of course, in order to calculate n, we must go back and calculate it through here, which means that in that case we must determine what this Fermi direct integral of order half is, whatever the value given a EF, of course. That is, if we know where the EF is, if we know the value EF, then we can determine n in general by using this equation always, but EF is 3 kBt energy below this value here, EC level, that is, if it is below that, then in that case we can use this approximation as here, n equal to NC e to power EF minus EC by kBt. All right, but why 3 kBt? Same old question. Well, if you are happy with 2 kBt, go ahead, use 2 kBt, that is approximation. So, that is a judgment you have to call based on what kind of approximation you want to make, what level of approximation you want to make, how much accuracy you want. In that sense, normally 3 kBt is a common, and it works fine. All right, let us now do the same thing for, let us evaluate also P, what the value of P will be, number of holes in valence band. For that, we will repeat the procedure exactly same thing. Whatever is in this box here, we will replace it by e to power eta v now. In that case, let us write down P. Therefore, P, so we will write again, if eta v is less than minus 3, then I can write P as being equal to NV e to power eta v, which means I can write P is equal to NV e to power, and you recall what eta v was. Eta v was EV minus EF by kBt. So, that was EV minus EF. So, that is our formula for calculating P in case this is true, which of course means that EV minus EF should be less than minus 3 kBt, which also means, this approximation also means therefore, that EF minus EV should be greater than 3 kBt, which means EF should be greater than EV plus 3 kBt. What does that mean? So, EF should be greater than EV plus 3 by kBt. That means, we do the same thing here to show you here that if this is EV and this is EC, then what should happen is that as long as if this is 3 kBt, as long as your Fermi energy is more than 3 kBt, that means on this side Fermi energy is higher than this line I have shown you, dotted line I have shown you, that in that case we are okay to use this formula. We are okay to use this formula in case Fermi energy is greater than 3 kBt from the valence band edge. It is higher than that. If so, then this formula will be used, which means that overall, if I summarize, so if I write the summary of this whole thing, then I will write it like this. This is 3 kBt and this is also 3 kBt. In that case, what happens? I can write in this region. When Fermi energy lies in this region, then I can write in this region, if Fermi energy is in this region, then I can write n as equal to Nc e to power Ef minus Ec by kBt, and I can write P as equal to Nv e to power Ev minus Ef by kBt. I can write it like this: Boltzmann constant times temperature. All right. So, these two formulas are valid in the region if you are 3 kBt away from the band edge. Such semiconductors are called non-degenerate semiconductors. Such semiconductors are called, when Fermi energy lies 3 kBt away from the band edge, then such semiconductors are called non-degenerate semiconductors. Notice, if your Fermi energy goes higher than this point, moves on this side, then what happens? In that case, I can continue to use this particular formula. Let us use another pen. Say Fermi energy is higher than this, I can continue to use this formula, I can calculate P according to this formula, but this particular formula will not be valid, because now I must use the Fermi direct integral. If Fermi energy goes on that side, then in that case, while because of Ef is still greater than Ev plus 3 kBt, so this formula for P is okay, but not for n. It is not okay for n, and I have to use then Fermi direct integral in order to calculate n. Similarly, if your Fermi energy is below this, if Fermi energy is below this point, this energy right here, which I have shown you as dotted line, in that case the formula for n is valid, then it is okay, because Fermi energy is below this dashed line. As long as Fermi energy is below this dashed line, this formula for n is valid, and hence this is okay, but then this will not be valid anymore. In that case, P has to be calculated using Fermi direct integral. All right. So, I hope you understand what this non-degenerate semiconductors mean. It means that Fermi energy lies 3 kBt, and 3 is obviously arbitrary here, you could make it 2, etc. But that's, now these are the formulas we will be using often, and you will see in most of our cases of concern to us, this condition will indeed be satisfied, that I will show you in few minutes from now. All right. So, now what else in this region? Let us continue on this non-degenerate semiconductors. Now, you should recall what I had taught you about Fermi direct function, that Fermi function, probability of finding electron at an energy level. Recall that we had said that when we are plotting this curve like this, Fermi function f of E versus energy, I had plotted something like this, that if this were Ef, then I had shown to you that at any temperature like this curve behaves like this, and I had approximated for E greater than Ef plus 3 kBt, we had approximated f of E as being equal to e to power minus E minus Ef by 3 by kBt, and we had approximated for E less than Ef minus 3 kBt, we had approximated 1 minus f of E as being equal to e to power E minus Ef by kBt. This is the approximation I had shown you earlier at some point of time, few lectures ago, couple of lectures ago, I had shown you this approximation. Notice the two are not two are same thing. That means for case of electron, in case of electron, when you are trying to calculate this n in conduction band, if Fermi energy is below this level, then all energies we are talking about, this E that we are talking about, if Fermi energy is below this level, then all energies we are talking about here, E, are indeed greater than 3 kBt, and therefore what happens is that I can use in fact, for Fe, I can use a classical distribution, a Maxwell-Boltzmann-like distribution. So, I can use this for conduction band, a Maxwell-Boltzmann distribution. Similarly, if for all energies greater than EV, greater than this dotted line I am showing you here, above EV, for that you notice that all energies here in the valence band where the holes are, that means this energy right here, this energy right here, this energy will indeed be, this energy E indeed will be 3 kBt below the Fermi energy. If Fermi energy lies somewhere above that, this line, in that case this EF minus 3 kBt, this condition will be satisfied. So, 1 minus Fe can indeed be approximated again by a Maxwell-Boltzmann like distribution right here, a classical distribution, that is, instead of Fermi direct distribution. The point being that non-degenerate semiconductor is, so if you substitute in fact for 1 minus Fe by this or Fe by this, you would directly, and you carry out the integration, you will directly get these expressions, which we have done later by approximating either that integral Fermi direct integral of order half to e to power eta. We have done later, but you could directly substitute under these conditions. You could substitute this F instead of Fe, for Fe you can substitute this, for 1 minus Fe you can substitute this expression, and you will get back these equations exactly. The point therefore means that an electron behavior of electron is somewhat classical when the Fermi energy lies in this range, and that's that. So, you can either think of this as a non-degenerate semiconductor or a classical semiconductor when the Fermi energy lies in this shaded region. Otherwise, of course, you have to use the Fermi direct distribution for Fe, the full distribution, and therefore, which results in Fermi direct integral of order half, and that has to be evaluated in that case. All right, I hope that gives you a nice good picture of what it is for non-degenerate case, for non-degenerate semiconductor, which I'll semiconductor I'll abbreviate like this, versus a degenerate semiconductor, exactly opposite of that. That means Fermi energy does not lie in shaded portion. In that case, we call it degenerate semiconductor. So, our formulas are N is equal to Nc times e to power E F minus Ec divided by kBt, and P as Nv e to power Ev minus Ef by kBt. That is our formulas for this. Otherwise, here N is equal to Nc times 2 by root pi Fermi direct integral of order half, and maybe if you wish I can write this as a function of now Ef minus Ec by kBt, because function of that eta c. So, I have substituted eta c in there, and P as equal to Nv 2 root pi Fermi direct integral of order half for Ev minus Ef by kBt. All right. So, these are the formulas. We will be clearly, I mean, for most of our cases, we will assume that Fermi energy, our semiconductor is non-degenerate, and we will be using these formulas. All right. Now, next question is, where is the Fermi energy? Where is this quantity? Where is Fermi energy? Unless I know Fermi energy, remember, okay, so let us just do one more thing by here. Now, Ev and Ec for a semiconductor are known, they are very well known. You may argue that how can you be so precise about Ev and Ec? Of course, they are always determined in reference to some common energy. So, some energy. That means, if you choose your reference to be of energy to be 0 here, then in reference to this value, then we know where Ev is, we know where Ec is. Those are the two numbers we know, because it is material property. And of course, notice this reference of energy is not important, because always you have difference of two energies involved in here, EV minus EF. So, if I determine EF, I have to determine, or I have to state EF what EF is, then I have to state that EF with respect to the same reference. As long as reference is same, and since we are dealing with difference of energies here, so therefore, where you choose your reference of energy does not matter. To that extent, depending on where reference you have chosen, with respect to that reference, we always know what EV, EC and EV are, since these are material properties. Since we know these, therefore, only question is, in order for me to determine, for us to determine what is value of n in conduction band, how many electrons that is are present in this conduction band, and how many holes are present in this valence band. How many means, whenever I say how many, I always imply per unit volume. So, everything is about densities. So, it is per unit volume, how many holes in valence band, per unit volume, how many electrons in conduction band. If you want to know, we need to state where the Fermi energy is. All right. So, let us do that. Let us try to first determine where the Fermi energy is. So, we will define some, we will first talk of intrinsic semiconductor. So, we will first talk of intrinsic semiconductor. All right, what is intrinsic semiconductor? This is a terminology you have heard right from your school days, that semiconductor being intrinsic and extrinsic. Remember, when it is doped, which we will cover immediately after this. So, what is intrinsic semiconductor? Often it is taught as if it said a semiconductor which is chemically pure is an intrinsic semiconductor. To some extent, such a definition may be okay. It may be okay, however, it is not always correct. What I mean by that is, there are examples such as, let us say, there are defect semiconductors, let us say zinc oxide, or for example, you can take gallium arsenide. They may be chemically pure, but still they have some defects. They have defects in there, they are point defects, for example, as an example, and these defects could be charged, and these charged defects could therefore, they could behave in a way as if the semiconductor was doped, and hence it is not always true to say that a chemically pure semiconductor is the intrinsic semiconductor, intrinsic semiconductor. More precise definition of an intrinsic semiconductor therefore is that n is equal to p. N is equal to p. This is basically the definition, that number of electrons in the conduction band is the same as number of holes in the valence band. Notice where I am drawing, by the way. Recall that we have something like this. The density of state goes something like this, and density of holes goes something like this. You will recall that this is what you had plotted earlier, and there, since this maxima occurred very close to the band edge, therefore, we always show all these holes lying right near the band edge, right below the band edge, and similarly for electrons, we show all these electrons located just above the conduction band, and that is point I had already made to you yesterday. All right. So, given this condition, and we say that if n is equal to p, what we mean is area under this red and area under this green curve should be equal. All right. So, where is that Fermi energy? You will recall such a situation occurred when Fermi energy was somewhere in the middle. I had shown the first picture when I showed the Fermi energy was smack in the middle, or not smack in the middle, somewhere in the middle. Then I had shown that these two curves are approximately equal. Approximately, I say, now we will be a little bit more precise. So, let us find out, let us say under this condition, in this case, let us give a special name to EF. We will call it intrinsic level. Intrinsic Fermi level, and we will give a name symbol EI. So, our question was, what is EF? So, we are now trying to determine what EF is. For intrinsic semiconductor, we state the definition is n is equal to p. We will use to determine use this to determine where EF is. And under this condition for intrinsic semiconductor, we are giving a special name to the semiconductor and we are calling it EI. In that case, of course, I will write n as equal to, I will use those formulas right up from here, write these formulas, we will use these formulas right here, n as being equal to NC times e to power EI minus EC by kBt, and we will use P as equal to NV e to power EV minus EI by kBt. In writing these equations, I have assumed the semiconductor is non-degenerate. Eventually, I will prove it to you that indeed this will be true. My assumption is not wrong. So, now if so, then let us try to determine EI by equating n and p. That means, if NC e to power EI minus EC by kBt should be equal to NV e to power EV minus EI by kBt, which implies, okay, so we do it like this, we take this on the left hand side, the exponential on the left hand side. So, I will write this as EI e to power EI minus EC minus EV minus EI, this whole thing divided by kBt. I am taking this on left side and writing it NV by NC, and now let us take log of it on both sides. So, what do we have? Of course, this is simplified here. So, we are going to get EI, then I am going to get 2 times of EI minus EC plus EV is equal to log of NV minus NC, which means EI is equal to EC plus EV by 2 plus half log NV by NC. So, what does that tell you? If let us repeat this one more time where EI is. So, EI, therefore, we will write EI as same thing, I am just repeating it, EC plus EV by 2 plus half log NV by NC. If this is EV, where does the Fermi energy lie for an intrinsic semiconductor, that chemically pure semiconductor, or in principle what should be read as, what we should be calling as n equal to p, where n is equal to p, where is the Fermi energy in that case? In that case, we find that Fermi energy is right in the middle. Where is this point? This point is right here, somewhere in the exactly in the middle. Exactly in the middle is EC plus EV divided by 2, exactly in the middle. Now, Fermi energy is not exactly in the middle, it is exactly in the middle in case if NV is equal to NC, in that case EI is in middle of, exactly middle of the band gap, right in the middle, precisely exactly in the middle is the Fermi energy. This is EI in that case. The dotted line is exactly the, in that case EI is this EI level which I am showing you here is exactly in the middle of the band gap. All right, but recall what NC and NV were. So, NC you will recall was equal to 2 times 2 pi ME star kBt by h square, not h bar square, keep that in mind, and NV was equal to 2 times 2 pi MP star effective mass of hole by h square 3 by 2. That means, if effective mass of electron was equal to effective mass of hole, then Nc and Nv will be equal, and this will be precisely in the middle, which means I can write this EI one more time. I can write this EI to be equal to Ec plus Ev by 2 plus half log of what? Nv, that means Mp whole effective mass, electron effective mass to power 3 by 2, or I can write this as Ec plus Ev by 2 plus 3 by 4 log effective mass of hole divided by effective mass of electron. So, I can write it in this form where EI is. So, EI is exactly in the middle if effective mass of electron and holes are equal. If not so, in that case, if they are not equal, in that case it is shifted from center by amount this. Indeed, this is a small amount, because if for most cases you have seen I have given you the effective mass in silicon or germanium, except in gallium arsenide where this may be slightly more, but in silicon or germanium indeed effective mass or of electron and holes are approximately equal. Some is 1, one is other one is 0.5. So, even this, then this number is a small number. So, the shift from the center is only a small shift. This indicates the shift from the center, whatever the center is, shift from that. So, that is what anyway. So, that is what an intrinsic semiconductor is. Okay. So, this is intrinsic semiconductor. That is what the by definition intrinsic semiconductor means. N is equal to P. In that case, Fermi energy lies in somewhere in the middle, slightly shifted according to the effective mass of electrons and holes, but nonetheless you can see we were justified to use the formula for non-degenerate semiconductor, because these band gaps are on order of what we are talking about, except if you are talking about something which is an infrared detector where the band gap has to be very small, or in that other than that we are talking about these band gaps to be on order of 1 electron volt or plus. More than that, in case of silicon it is 1 electron volt, in case of germanium it is 0.66 electron volts. So, in 3 kBt is 29 milli 3 kBt at room temperature is 29 milli electron volts. So, 3 kBt, let us say 100, let us say about 100 milli electron volt per or 0.1 electron volts. So, as long as we are about 0.1 electron volts away from the band edges, we are okay to use non-degenerate semiconductor statistics at room temperature, and clearly since EI lies in the middle and band gaps are about on order of 1 electron volt, hence we were justified in using those formulas for non-degenerate semiconductors. All right. So, this is all about intrinsic semiconductors. Now, so now let us do this. So, what is N we have still not determined. We have determined N equal to P. Now, once we know EI, we should be able to determine what N is equal to. All right. So, what is N equal to? Let us find out. In fact, that we will let us do in a minute afterwards. In fact, let us do this. Let us make general comments for. We will determine Ni. Just hold on first. General comments for semiconductors which may or may not be intrinsic. They may be intrinsic, they may not be intrinsic. Okay. First comment I would like to make is this product of N and P. Remember, I am not assuming that it is necessarily intrinsic now. So, it may be intrinsic or may not be intrinsic. So, N product N and P is what I want to know. So, NP. NP is equal to Nc e to power Ef minus Ec by kBt. multiplied by NV e to power EV minus EF by KBT. I am assuming non-degenerate semiconductor, I am continuing to assume that. We will always assume this in this class from now on, unless specified otherwise. All right. So, let us look at this NC NV e to power, now EF will cancel out, and what I am going to get is minus EC minus EV by KBT. So, what do we have? We have this as NC NV e to power minus EG by KBT. Notice this is a constant. Notice that this is a constant. Why? NC is a material property, NV is a material property. Let us take a look. NC was defined right here. What is there? There is temperature, Boltzmann constant, this Planck's constant, all these are constants. Once you say a material silicon, then effective mass of electron gets fixed. Similarly, effective mass of hole gets fixed. That means, NC and NV get immediately specified the moment you say, you name the material. The moment you say silicon or gallium arsenide, these NC values of NC and NV are specified, and we have calculated those. So, that means, and also the moment you specify the material, band gap becomes known. The band gap is also independent of EF. Remember, this product has become independent of EF. EF was the only quantity we did not know. The moment you specify the material, EG is known, NC is known, NV is known, and therefore, it is a fixed number. Whatever the Fermi energy, wherever there is a Fermi energy, product of NP is a constant. Product of NP is a constant. That is a very important result, and that is a general comment. That means, semiconductor may be intrinsic or semiconductor may not be intrinsic, does not matter for all semiconductors as long as they are non-degenerate semiconductors. This must be true, that this product NP must be constant, which means I need to, as long as I know this constant, I need to determine only one of them. I can determine N, then immediately, since product NP is constant, therefore, I can immediately determine what this other P is. If we know P, then we can immediately determine what N is. Since in intrinsic case N is equal to P is equal to Ni, we are giving it a name now, just like we had given a, for EF we had called it EI, we had given it a name of EI. Similarly, we are calling it intrinsic carrier concentrations. Number of electrons or number of holes per unit volume, that is for a semiconductor which is intrinsic. If it is an intrinsic semiconductor, then in that case N is equal to P is equal to Ni. That means, product NP is equal to Ni squared. That means, since N is equal to P and the both our values are called Ni, this must be true. Therefore, NC NV e to power minus Eg by KBT. What does that mean? That means, since this, remember, this is a material property, the moment we say silicon, this number is fixed, and since this is fixed, that means this quantity is also fixed quantity. That means, say fixed quantity once we specify the material. If we say silicon, Ni is fixed immediately, all right, and this is always true. In intrinsic case, Np is equal to Ni square, and since product Np is always constant, that means, in all semiconductors, whether semiconductor is intrinsic or not intrinsic, product Np should always be Ni square. This product Np is Ni square, whether or not semiconductor is intrinsic or not. In case of intrinsic, it is indeed Ni square, that is obvious, but since product Np is constant, it is the same whether it is intrinsic or not. Therefore, or rather since it is constant, and in special case intrinsic semiconductor is Ni square, that means, in all cases it should be equal to Ni squared. Now, with this, two results therefore, I have. One is that now Ni, one result I have written here itself, This is the result number 1, that product Ni, general result is that Np, product Np is equal to Ni square, and I can now determine what intrinsic electron concentration is also. I can now write this as square root of Nc Nv e to power minus Eg by kBt. So, I can determine by 2 kBt, sorry, as I determine Ni. So, these are the two results which I have. I can determine Ni, and I have already written this as a general comment, and I can determine Ni. You recall from here there is a t to power 3 by 2 dependence on this. So, therefore, this t by 2 in Nv and Nc. So, when I am writing this as follows, so this would have a dependence of this would have a dependence of t to power 3 by 2 t to power 3 by 2 dependence will show up here also, and the temperature dependence will show up here as well. Now, third statement I want to make is, in general, since I now know Ni, I can use this. Well, Ni is a material property. Since once I specify silicon, I know what Ni value is. I can use this as a reference to calculate N in all other cases. Since N is equal to Nc e to power Ef minus Ec by kBt, and Ni is equal to Nc e to power E I minus Ec by kBt. Remember, when Fermi energy is Ei, then electron concentration is Ni. These two equations imply that N, use these two equations, and you can write therefore Ni as e to power E. I can write this as, use this. So, I can write N equal to Ni times Ef minus Ei by kBt in general. And similarly, so this is what I will, so N can be determined as follows. In general, N can be reference to N, instead of Nc, I can write it in reference to Ni, and I can write this as Ni times Ef minus Ei by kT. Similarly, I can write P as equal to Ni times e to power E I minus Ef by kBt. You can derive this one also just by same method. So, N and P can be written in general. In general, this is not for intrinsic semiconductor. When Ef is equal to Ei, then of course, N will come out as Ni. Otherwise, given what Ef is, then you can, in reference to Ni, you can determine what N is. So, these are some of the formulas which you could remember. Now, so this few things which I want to point out, these are general comments. They apply to all semiconductors, whether they are intrinsic or not. Now, let us calculate Ni. What is the value of Ni? Ni value is Nc times Nv e to power minus Eg by 2 kBt. All right. So, you know the band gaps. You have been given the band gaps for different materials. You know what Nc and Nv is. This is also given to you. So, at room temperature at 300 K, let me give you some numbers. Ni is equal to about 2 into 10 to power 6 per centimeter cube, number of holes and number of electrons in conduction band and valence band for gallium arsenide, which has a band gap of about 1.5, and this is about 1 into 10 to power 10 for silicon, and this is about 1 into 10 to the power 13 per centimeter cube for germanium. What do you see? So, these are the values for Ni. That means, in the semiconductor, this many electrons per unit volume, of course, will be present in valence band, and this many holes will be present in the electrons in the conduction band, and this many holes in the valence band would be present. Notice that as band gap decreases, this number increases. Germanium has a band gap of 0.66, about 1, about 1.5. So, band gap is increasing and this number is decreasing, which is fairly obvious, as you can see here. There is a Eg minus Eg in there. Higher this number, smaller this Ni would get. So, if I plot this like this as a function of temperature, actually, if I plot this as a 1 by T and I plot Ni, or if you wish log Ni, then what I will get is something like this, a curve which looks something like this. This is the plot of Ni. I will leave it at not Ni, but I will leave it at log of n, the carrier concentration n, number of electrons in conduction band. Then in that case, this is the for intrinsic semiconductor, then this equation will be valid. This equation will be valid for intrinsic semiconductor, and I am going to get a straight line. If I take log of Ni, if I take log of Ni, natural log, then it will have a slope of Eg by 2 kb. So, the slope will be Eg by 2 kb, right. So, this could be a method of determining a band gap. That means, if you measure, for example, if you measure this carrier concentration, of course, you can notice that why is it straight line? This is straight line is because you see there is a temperature dependence here, there is a temperature dependence right here also, but this is much weaker temperature dependence in Nc and Nv, has a much weaker, and that is why I was pointing out to you this temperature dependence. Since this temperature dependence is much weaker than the exponential temperature dependence, therefore, this curve looks more or less a straight line. If instead of n, if you were to plot instead of log n, you would plot log of conductivity, and remember conductivity would be, you go back to our ideas of conductivity, we had said that conductivity would be equal to number of electrons, charge and mobility of the carriers. So, if instead of n log of n, if you plotted log of sigma, then Q obviously does not have a temperature dependence. Temperature dependence of n is already stated here, right here. Then if mu has certain temperature dependence also, it turns out that temperature dependence of mu is as temperature increases, this quantity decreases, mu decreases, which I will talk about eventually, and as temperature increases, Nc and Nv increases, this quantity mu decreases. In fact, sensitivity to conductivity, therefore, as a function of 1 by T becomes even less, and the straight line becomes even more straighter. Therefore, if you were to plot conductivity, and conductivity is relatively easy to measure. So, if you instead of log n, if I plotted log of conductivity, then notice this could be a method, and you measured it as a function of temperature, then this could be a method to determine what the band gap is, Eg is, because the slope will divided by 2 kb will give you the band gap. All right. So, this is what I wanted to tell you all about intrinsic semiconductor and also the general comments. So, remembering this, we will start using now from the next lecture, we will start with extrinsic semiconductors, that means semiconductors which are doped. But before I do that, maybe I make one more comment before I close this. Now, let us look at this Ni value actually, let us look at these numbers also, these numbers which are Ni which you have determined. Remember how many bonds are there in let us say silicon, in silicon or for that matter in other cases also, we have about 5 into 10 to power 22 atoms per centimeter cube. Each silicon has 4 bonds, each silicon has 4 bonds with other silicon. Remember that crystal structure for silicon was shown with tetrahedral bonding. So, multiply that by let us say 4. So, that means about 1 into 10 to power 23 bonds per centimeter cube, that number of bonds. So, if I have this many bonds and in intrinsic conditions at room temperature, if I have 10 to power 10 in here as the intrinsic carrier concentration, and if I think that each bond breaking leads to one electron going up here and creating a hole here, if that is what the process is, that because the bond breaks, an electron goes to the conduction band leaving behind a hole, then I am having about 10 to the power 10 bonds in silicon at room temperature which are broken, which means we can expect. So, about since Ni is about 10 to the power 10 per centimeter cube, that implies 1 in bond per 10 to the power 13 are broken. So, that is the order as to how many bonds are broken in silicon at room temperature. Of course, this number could not have been very large. If it were very large and a huge majority of the bonds were broken, then obviously this won't remain a semiconductor at all. It won't remain a material, not semiconductor. I should say it won't remain a material with all the bonds broken. All right. So, with this, let me close this topic today of intrinsic semiconductors and the general comments which apply to all semiconductors, intrinsic or not. And from next lecture, we will start with extrinsic semiconductors, namely the doping of semiconductors. Thank you.